Hi students, myself M.V. Sudarshan, Associate Professor, Department of Electrical and Electronics Engineering, and I am going to teach you the course Power Systems 2 in this third year first semester, and it is a sequel of Power Systems 1 which you have studied already in second year first semester. Before going to the course, let us see the overall view of the electrical power system network. In general, the electrical power system network is divided into three categories as generation, transmission and distribution. These three categories of power system network is shown in a pictorial diagram here. If you see it, this one is the generating station where the electrical power is generated, and the various different types of power plants are studied in the previous semester in the subject called Power Systems 1. And next, the part which is enclosed within this green color is the transmission part, where the electrical power generated in the generating station is transmitted from generating station to the utility point. And coming to here, the third part, if you check it here, this is the distribution, where the entire electrical power transmitted will be distributed to the residential loads and bulk consumers. So this is the entire layout of the electrical power system network, where we are seeing the generation where the electrical power is generated. This is the transmission part, transmitting from the generating station to the utility point, and this is the distribution where the electrical power is distributed at lower voltage levels to the household purposes and also for the bulk consumers. So the course called Power Systems 2, it is a sequel of Power Systems 1, because in Power Systems 1 we have already studied how the electrical power is generated and what are the different types of electrical power plants. Here in the Power Systems 2, it entirely deals with the transmission part. In detail, this transmission part is divided into two subcategories. They are the primary transmission and the secondary transmission. So observing here, this electrical power generated in the power stations is boosted up its voltage level from 11 kV to 220 kV or 500 kV. So such a 220 kV or 500 kV is transmitted with the help of three-phase three-wire system. So the line which is transmitting the voltage at a very high voltage is defined as primary transmission. So after transmitting the electrical power over a distance, again using the transformer, the voltage level is somewhat reduced from 220 or 500 kV to 132 or 66 kV. Such a line, whatever the power is transmitted with this 132 kV or 66 kV comes under secondary transmission. So combinedly, the transmission is done at very high voltages, which are not the voltage ranges of our utility point. In general, the utility that is called residential loads requires a single phase of 230 volts only, whereas the bulk consumers requires a voltage of only 440 volts if it is a three phase. But here, the transmission is not done either at 230 volts of single phase or it is not done at 440 volts of three phase, but it is done at very high voltages because of having more number of advantages. In later coming sessions, we will see the advantage of having that transmission done at high voltages. So after that, again using a transformers, this 66 kV voltage is stepped down to 11 kV. So from here onwards of this 11 kV, it will be distributed to the load points. If at all, if the load points are of bulk consumers, then we will supply directly that 11 kV to that bulk consumers. They will put their own transformers and they will step down that 11 kV voltage to 440 volts. Such a bulk consumers are called primary distribution. And next, using the street side transformers which are located on the plinth, if you can observe in the straight sides, we can see them, or if they can be observed on the H-pole type structures also. So using that distributed transformers, there the voltage level is stepped down from this 11 kV to 400 volts or 230 volts. So again, after stepping up down to that 400 volts or 230 volts, that power is distributed to the residential loads. Such a distribution is called as secondary distribution. Finally, observing this layout diagram, total the electrical power is generated in the generating stations, transmitted at a very high voltages in the transmission part, distributed in the distribution section up to the utility point of utilization, that is 400 volts or 230 volts. And coming to the next, this is the single line diagram representation of an electrical power system network. In this single line electrical diagram, we represent the same power flow from the generating stations to the utility point in terms of electrical representations. Like previous layout, we have shown the transformer with the block diagram and the towers are shown here, and the transmission line is shown with the 3-phase 4-wire system, etc., etc. But now in this diagram we are going to show the entire electrical power system network in a electrical representations. Like this is the symbol for an alternator, where the alternator is a heart for the generating station, which generates a voltage of 11 kV. As I told you, using the step-up transformer, which is located in the premises of the power plant, it will boost up the voltage from the 11 kV to 132 kV. Such a substation we can call it as add substation. There the voltage is increased from 11 kV to 132 kV and it was transmitted over long distances. Such a transmission of the high voltage is called as primary transmission. As here you can observe the primary transmission done at 132 kV, which we are going to see in detail in the coming units. And coming to the next, after transmitting this electrical power over certain distance, again a step down transformer is used here, which step downs the voltage of this 132 kV to 33 kV. That 33 kV will be transmitted in the transmission line for certain distance. Such a line is called as secondary transmission. As here you can observe that it is a secondary transmission line which transmits the power at 33 kV voltage. And later, whenever the power is, whenever the transmission lines are reached nearer to the cities or outskirts of the towns, there we will use again a step down transformer in the substations. Yes, in the substations, there this 33 kV is stepped down to 11 kV. So the line which is operating with a voltage of this 11 kV is called primary distribution, as I told you in the layout diagram. So this is the distribution part where the primary distribution happens at comparatively larger voltage called 11 kV. So those load points are called as bulk consumers. Using by their own transformers, they will reduce that 11 kV to 400 volts. And finally, using distribution transformers, where it was located in the street sides, that 11 kV voltage is stepped down to 400 volts. That 400 volts will be distributed among many consumers for the residential loads. Such a line operating with 400 volts is called as secondary distribution. So here you can observe that it is a secondary distribution where the voltage is distributed at 400 volts level of 3-phase supply or 230 volts for a single phase supply. So previous diagram and this diagram both are same, but it is a general layout, but here it is a electrical representation with a single line diagram. Finally, I conclude that the electrical power system network consists of 3 categories: generation, which you have already studied in the previous semester with the subject of PS1, and next transmission, 2 subcategories: primary transmission and secondary transmission, which we are going to study in this semester with a course titled called Power Systems 2. And next in the coming semester, we will discuss about the distribution in a subject called Electrical Distribution Systems EDS. After getting an overview of this electrical power system network, let us see what is the exact objective of this Power Systems 2 course. So the objective of the Power System course is, first, to transmit the electrical power, we have to model the transmission line mathematically. The mathematical model of the transmission line includes the transmission line and modeling in terms of basic primary passive elements called resistor, inductor, capacitor, and shunt conductance. Using these 4 elements, we will model the transmission line. So after modeling the transmission line, the next objective is we have to analyze its performance considering 2 parameters, like analyzing the performance of the transmission line in terms of its transmission efficiency, where we should take care to transmit the electrical power without power wastage, so that we can say that its efficiency is very good. So we have to transmit the electrical power with lesser power losses, so that we can say it is more efficiently operated. And next parameter to be consideration is voltage regulation. At the same time, voltage regulation should also be taken into care, where the voltage should not be dropped from sending end to the receiving end. In terms of these 2 parameters, we have to analyze all transmission lines in the power systems 2 subject. That is our second objective. And the third objective is, after analyzing the performance, we will put it in the operation. Whenever it was placed in the operation, then we have to check the transient behavior of that power system line network at different conditions, switching operations and abnormal cases, with the help of the concept called traveling waves. And next, another objective is to understand the mechanical design aspects of the transmission lines in terms of how to design the towers, height of the tower, width of the cross arm, and how much sag is to be provided, etc. And also finally the objective is to design the insulators which isolates the live wire with the tower structures. So the overall objective of the course is to transmit the electrical power from the generating stations to the utility point in an efficient manner by decreasing the losses and also by decreasing the voltage drop. These 2 should be very clear. That is, it leads to the improvement of transmission efficiency, and also it operates at better voltage regulation conditions. One more point here we have to discuss is, in power systems 1 subject previously, we came to know that the generating stations are located in a very remote places. It is very far away from the consuming points. So since it is very far, transmitting such an electrical power from that remote locations to the utility point is a major task without wasting the power. That is why this power systems 2 objective is to transmit that electrical power from a very remote places to the utility points without wasting the power. Next, coming to the course outcomes. So as all of us know that every subject will consist of 6 units. With each unit, after completion of learning, we will get an outcome. So here I am giving you to 6 outcomes, course outcomes. The first course outcome is from the first unit, where we will model the transmission line from the 4 parameters. As I told you, they are resistor, inductor, capacitor and conductance. So modeling of the transmission line is done in that first unit. So after completion of the first unit, one can model the transmission line. After modeling the transmission line, the mathematical analysis is done, which gives the performance of that lines. The lines are categorized here into 3 categories based upon the distances. So they are short transmission lines, whose length of the transmission line is about up to 80 kilometers length, and medium transmission line, whose length is about from 80 kilometers to 240 kilometers length. Such a line can be called as medium transmission lines. So in the second unit, as a course outcome, after completion of that second unit, we will be analyzing its performance of short and medium transmission lines. And coming to the course outcome 3 from the third unit, the same performance can be evaluated for long transmission lines. These long transmission lines are the transmission lines whose length is greater than 240 kilometers. So in the first unit we modeled the transmission line. In second and third unit we will get an outcomes of how to analyze the performance of the short, medium and long transmission lines. After the completion of the fourth unit, we will get the fourth outcome, that is understanding the concept of traveling waves, which will be helpful for finding out the transient behavior of the transmission line. Next, after completion of the fifth unit, we will get an outcome from the fifth unit, that is, whenever the transmission line is placed in the operation, such a line is called as charged transmission line. Whenever it is charged, it will be affected from external factors like lightning strokes and will have certain factors like skin effect, proximity effect. Then how the transmission line is operated considering all these factors will be able to understand after the completion of the fifth unit. So it was the outcome of the fifth unit. Coming to the outcome of the sixth unit as CO6, course outcome sixth. Here finally, considering all parameters so far what we have learned, we will design a tower, electrical tower, where the conductors are to be hanged to transmit the electrical power at certain height from the ground level. So we have to fix the height of the tower, and also we have to fix the length of the cross arm. So fixing the height of the tower and cross arm length is nothing but the mechanical design. So that we'll be able to understand the mechanical design of the transmission line by providing how much sag, and also finally we'll be able to know the interior design of the insulators. The purpose of the insulators, as all of us know, that it has to isolate the line conductor with respect to the tower structure. These are the total 6 outcomes from the 6 units. And next here, coming to the syllabus, as I told you, 6 units are there. Which are these 6 units? Line parameters, where 4 parameters are to be evaluated. Among those 4, resistor and inductor forms the series impedance as Z, which can be written as Z is equal to R plus J XL. And 2 more parameters are learnt in this first unit. They are shunt parameters, they are shunt capacitance and shunt conductance, where you can identify it as a shunt admittance Y. So calculation of all the 4 parameters will be discussed in the unit 1. And next in the unit 2, as I told you, the performance is to be evaluated for short transmission lines and medium transmission lines. And next in the unit 3, we are going to study the performance of the same long transmission lines. And next in the unit 4 is related to knowing the concepts of the traveling waves, which will be helpful to analyze the power system transients. And next in the unit 5, we are going to see the various factors which will affect the performance of the transmission line. And here some of the effects we can recall here as skin effect, proximity effect, Ferranti effect, etc. And next, coming to the last unit, 6th unit, we will design the tower structure by calculating the sag, which directly helpful for us in fixing the height of the tower. And next, we will see in detail in the 6th unit about the design of the insulators. So far we have seen the layout of the electrical power system network and a single line diagram of the electrical power system network, how the power is reached to the utility point. And next, we have seen the course objective. The single objective of this course is to transmit the electrical power with higher efficiencies. And next, we have seen the course outcomes, which are defined 6 outcomes from the 6 units. And next, we have seen what are the units that we are going to study in this course. And next, we will see the very heart of this course, that is, what is the exact necessary. If you see the layout, in the layout if we recall them, there we can observe the voltage is generated at 11 kV, utilization is done at 400 volts, but in between these two generating stations and utility points, either of the voltages are not available. We are operating the entire transmission network or distribution network other than these 2 voltages. I mean to say very high voltages are used here for operation. Then what is the necessity? We are increasing up purposefully. Again, whenever we want to use the voltage, we are decreasing it. What is the necessity of increasing the voltage and decreasing the voltage? Why not we directly generate 400 volts? Or why not we use this 11 kV for the entire transmission and distribution? What is the exact necessity of transmitting the power at high voltages? We are going to discuss in this session. So in this at this point we are going to learn what is the exact necessity of the transmission lines operating at high voltages. Whenever the transmission line is operated at high voltages, we are having many advantages. Like the first and foremost advantage is it reduces the transmission copper losses, which is very important. So to have an efficient power transmission, the power loss should be minimum. We can minimize or we can reduce that copper losses during transmission if and only if the voltage is very, very high. In a clear view, if you check it, the power P which is going to be transmitted can be given as 3 V phase I phase cos phi. This is the power which is to be transmitted, and the copper loss which we have to minimize is given by formula 3 I phase square into resistance of that phase. So substituting the value of that I phase from the power value, we can rewrite this copper losses as copper losses is equal to 3 P square by 9 V phase square and cos square phi. From this equation it is clear that the copper losses are inversely proportional to square of the voltage for a given amount of the power to be transmitted and defined amount of the nature of the load. So the copper losses is inversely proportional to square of the voltage. That is why to minimize this copper losses to a very, very minimum value, since it is inversely proportional to the square of the voltage, we are increasing this voltage to a very, very high values. That is why to have an advantage of this first one, to reduce minimum copper losses, to reduce the copper losses, we are boosting up the voltage at very, very high voltages around 500 kV. And next, second advantage is directly, if you decrease that copper losses, it will lead to the direct increase of transmission efficiency, because efficiency is inversely proportional to the copper loss. If the copper losses are minimized, then the efficiency will be increased. And next, the advantage is, third one is, it requires less amount of copper material. The amount of the copper material required to transmit the power will be minimum, because as we know that volume of the conducting material required is equal to area into length. So here, by increasing the voltage, the currents get decreased, which requires a very less smaller cross-sectional area. Since the cross-sectional area is very small, obviously we will have lesser volume of the conducting material. That is the third advantage. And the fourth advantage is, since smaller cross-sectional area is used, volume gets decreased. And next, the resistance of the material, as we have designed it for to be very low, and the current's magnitudes has been fallen down because of high voltage operations. So the product of this I and R is called as ohmic drop or voltage drop. Therefore, I is small, and purposefully we have designed the resistance to be small for the conducting materials. Therefore, the product of this I and R decreases the voltage drop. If the voltage drop is decreased, it leads directly to the better voltage regulation. Operation of the transmission lines at better voltage regulation. The voltage regulation is nothing but giving a stiff voltage whatever the load is required. That is as per the demand of the utility. So in the advantages, it is very clear that two keywords, they are transmission efficiency and voltage regulations are the two keywords. The ideal values of this transmission efficiency and voltage regulation are, transmission efficiency must be equal to 100%, it's an ideal value. And the voltage regulation must be 0%. We have to design a transmission line such a way that its efficiency should be 100% as well as its regulation should be 0% in the ideal case. Otherwise, we will design the transmission line such a way that these two values will be nearer to them. So this is possible if and only if the copper losses are minimum, and this is possible if and only if the drop is minimum. So the advantages of high voltage transmission is nothing but copper losses are minimized, which the first key point called transmission efficiency can be approached to unity ideal value called 100%. And here voltage drop is also minimized, where you can get the better operation with good voltage regulation. So that is why all the transmission lines are operated at very high voltages. Anyhow, for any system there will be pros and cons. So far we have discussed the advantages of the transmission lines operating for high voltages. At the same time, on the other side, there are some drawbacks. Whenever the transmission line is operated at high voltages, the first drawback is it increases the transmission cost, because to transmit the electrical power at a very high voltage, the live conductors are at high voltages, which is to be separated from the ground level with a suitable height. So the tower structure should be increased in terms of its height, which will increases the cost of the tower, because more material is to be used for that tower. If you use less voltages, if you operate at less voltages, obviously the clearance will be minimum, so that the height of the structure will be minimized. That is why if you see there, the transmission network entire, you can observe the towers which are very height in structures, as because they are operated with 132 kV or 220 kV. Whereas in the distribution side, if you see 400 volts line, they are not like a tower structures. They are simply wooden poles, concrete poles with only small heights like this, cross arms like this. So the tower structure increases if the line is operated at higher voltages. That is the first drawback. And next, if the line is operated at very high voltage, it will be affected with a parameter called corona, which is different from our actual situation what we are facing now. So this corona you can observe in our electrical power system network also. Whenever it is operated at very high voltages, the line around the wire, the air will be ionized. After ionization of the air around the conductor wire, you can observe some violet glow in that conductor. After that, you can observe some hissing noise around that conductor. And next, if you leave that case, it will lead to the production of the ozone gas. If these three are observed over a transmission line, then we can say that the conductor or the transmission line is affected with a corona, which increases, this corona discharge will increase the power losses. One side we have decreased the power loss due to copper, that is copper losses. Power losses we have decreased. But here, the same power loss you can observe because of this corona, which happens at very high voltages, because to ionize the air around the conductor, it requires a sufficient amount of high voltage. Since we are transmitting the power at high voltages, it may lead to further corona discharges. Anyhow, this corona discharge can be minimized by using bundled conductors. Bundled conductors. So these two are the drawbacks. Anyhow, we will compromise for these two drawbacks in terms of cost and in terms of providing bundled conductors, so that we can have the previous advantages. That is why the entire power transmission lines are done at very high voltages. So coming to the summary of this today's class, we are going to learn the course called Power Systems 2 in this semester 3-1, where the single line objective is to transmit the electrical power with higher efficiencies and better voltage regulations, that is with a voltage regulation approximating to 0. This is the single line objective of our course. Whatever you want to do, you do it and transmit the electrical power with higher efficiencies and with better voltage regulations. As I told you, the ideal value of this efficiency is 100%, and methodologies are implemented here to transmit the electrical power to such a way that its efficiencies will be nearer to 100%, and also methodologies are implemented to minimize the voltage drops, so that we will have a good voltage regulated lines. And also we have seen the course outcomes, 6 course outcomes for 6 units, And finally we have seen the necessity of transmitting the power at high voltages because it reduces the copper loss, since copper loss is inversely proportional to square of the voltage. If the copper losses are minimized, obviously the efficiency will be increased, which our first point is fulfilled. And next, with the transmission of the high voltage, the volume of the conducting material gets decreased. And next, the drop called voltage drop will be minimized, which leads to the better voltage regulation. Our second point is also fulfilled. And in the next coming classes, we are going to see the unit 1 in detail, which is nothing but transmission line parameters.